Hello! In this video we'll look at recursive function calls, that is, functions that call themselves. To handle saving and storing registers, a recursive function call needs to pay close attention to what it needs to save. So again, a recursive function call is a function that calls itself, and when I'm converting it to assembly language code, I like to do a first pass where I just treat it as if it's calling a different function and ignore the overwritten registers, and then go back and think about how to save and restore the registers on the stack as needed. So as a classic example of a recursive function call, imagine the factorial function, factorial of n, also written as n exclamation point, which is n times n minus 1 times n minus 2 times n minus 3 all the way down to times 1. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. Here's a recursive definition of the factorial. If we want to do factorial of n, we see if n is less than or equal to 1, we'll return the base case of 1. Otherwise, we'll return n times factorial of n minus 1. So let's say our main function called factorial with n equals 3. Factorial of 3 will return 3 times factorial of 2. To find factorial of 2, we see it should return 2 times factorial of 1. And factorial of 1 will return 1. So now we come back up. Factorial of 1 was returning 1, so factorial of 2 is returning 2 times that 1 makes 2. And factorial of 3 is returning 3 times factorial of 2, which is 6. Let's take a look at how to code this. So again, on our first pass, we'll treat it as if we're just calling another function and ignore the stack. And we get the black code. So factorial, we need to see if n is less than or equal to 1. So we'll put 1 in T0. We'll do a branch on the opposite condition. So we're interested in less than or equal to. So we'll do a branch on greater than. If n is greater than 1, we'll go to else. Otherwise, we want to do the body. And the body is add I A0, 0, 1. We'll put a 1 into our return register, A0, and we'll jump back to the return address. If n was not less than or equal to 1, then we want to do the else part, where we need to do n times factorial of n minus 1. So we need to put n minus 1 into the A register by adding the old value of n and minus 1, put that in as our new argument, and then we'll jump and link to call factorial. When we return, we'll multiply our n times the return result, and A0 is our return result. T1 is going to be the n that we get back, and we'll look at restoring that in a moment. Let me say this again. T1 is the n that we had back. A0 is the result of calling factorial of n minus 1, and we'll put that in A0 to be the return result from our factorial, and then jump back to RA to return to the caller. So that's the main logic. Now let's look at saving and restoring registers. So anytime factorial is going to call itself, it needs to save the return address register because we need to know where to go back to before we change it with a jump and link. And we also need to restore, or we need to save our value of n because we're going to change it when calling factorial. So let's make room for 2 registers on the stack. We'll save away A0 and RA on the stack. Now, if we don't have a recursive call, we'll just restore the stack pointer, and there's nothing else to do. But if we are making the recursive call to factorial, then when we come back, we need to restore the value of n. But n had been stored in A0. Now factorial of n minus 1 returned its answer in A0, so we'd better not put n back in A0. Instead, let's put it in T1. We'll also restore RA, so our factorial knows where to jump back to, and we'll add 8 to the stack pointer, and that way clean up the stack. And now here at the multiply, we're going to make our result be n, which is now in T1, times the result of factorial of n minus 1. So suppose this factorial function began at address 8500 in memory, then the jump and link is at 8524, and we want to store 8528 in the RA register as the place to come back to from each jump and link. So imagine we're following the stack frames as we do this call. So suppose the stack pointer is initially at FF0, and we begin our call. So on the first time we call, we'll move the stack pointer down to FF8, and we'll put A0, which was 3, n of 3, and the return address, say, to the main function that called factorial of 3. Now factorial of 3 is going to call factorial of 2, and so we need to move the stack frame again to FF0 and store away A0 from the second call, which is now 2, and the return address, which is now 8528, or to return to factorial of 3. Now factorial of 2 is going to call factorial of 1, so we need to store away A0, which is the value of n, of 1, and the return address, 8528, of where to return to from the call to factorial of 2. Now, when we're all done, factorial of 1 will return the value 1 and bring the stack pointer back up here. Factorial of 1 will get factorial of 2 will pull off its value of n of 2, multiply it by the 1, put its answer as 2, and return to the address that was here. Bring the stack pointer back up. And now we're in factorial of 3 again, which will multiply its n of 3, recovered from the stack, times the 2, returned by factorial of 2, to get an answer of 6, and we pull off its return address so it can return to main when it's done, and before it does that, it'll bring the stack pointer back up to FF0 where we began.